Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's our great pleasure to have Oscar Al from Hong Kong UST to come to Microsoft Research and give us a talk on video denoising. Oscar got his PhD from Princeton University in 1991, and then he became a faculty member in Hong Kong UST in 1992, where he is currently a director of Multimedia Technology Research Center and advisor of a computer engineering program in Hong Kong UST. Oscar is a veteran in MPEG and the H.264 series video standard, and I have read many good papers from him and his group. And now he has been serving a number of distinguished positions in the society. For example, he is associate editor for IEEE Transaction on Circuit Systems, Part 1, and IEEE Transaction on Circuit System Video Technology. He's the chair of the Technical Committee on Multimedia Systems and Web Application, and has held many distinguished positions. Without further ado, let's hear Oscar's talk on video denoising.
Thank you, Jin, and it's great for me to be here. Okay, my honor to be here. And I just want to show this picture, a warm welcome, warm hello from Hong Kong. Okay, so we're on the other side of the globe. Okay, right now Hong Kong is still 20-some degrees. See, we use Celsius, 20-some degrees Celsius. I think it's probably 70-some. Degree F. Okay, so compared with here, we're quite a bit warmer, and the weather is nice. Okay, and we are fortunate enough that this is the university. The picture in the center is actually the university, and it is quite pretty. Okay, and these are some attractions, tourist attractions there. Okay, so we have Disney World with the Ocean Park and stuff like that. So it's kind of interesting. Okay, if you haven't been to Hong Kong before, I would love to invite you to come and visit us too in the university. Okay. So our university is actually quite pretty, so that's kind of nice. Okay, all right, I'm going to go and start the talk. Okay, all right, so my name is Oscar, and I'm from Hong Kong, okay, HKUST, okay. I am with the Department of Electronic and Computer Engineering, okay. What I'm going to show you today, video denoising, is basically the work done by my student, Li Wei Guo. He has just finished his PhD, and his whole thesis is actually on video denoising and video modeling kind of thing. Okay, all right. So this is what I'm going to do today. Okay, talk a little bit about motivation. Talk about contribution. Basically, we'll be talking about a multi-hypothesis motion compensated filter. Okay, we'll talk about noise robust motion estimation for temporal denoising. Okay, and then integration of temporal denoising and hybrid video codecs, and then I'll come to some conclusion and perhaps some demo. Okay, but actually, you know what? I think I'm going to go to the demo first, because this helps to motivate people to understand what they're talking about. Okay, what we're talking about here is basically like, okay, if you look at this video, okay, this is the regular common test sequence called Akio, and we've added noise to it, and when you look at this video, okay, all right, it has a lot of noise, yeah, okay, unpleasant, people don't like it, okay. Not only is it unpleasant, a big problem about noisy video is that it costs you a lot of bits to compress. It costs you a lot of bits to transmit as well, and this is all undesirable, okay. Not only that, imagine when you do compression, for example, MPEG, H.264 kind of thing, basically what you need to do is you need to do something like motion estimation, DCT quantization, and stuff like that. Okay, imagine doing motion estimation with this kind of video. Okay, with all the noise flashing and everything, you're going to go into a lot of difficulties, and very often the motion vectors that you get out of this kind of video is going to be pretty bad, all right, and costing you quite a lot of bits to encode. As a result, what we are talking about is, hey, can we remove this noise? Video denoising. Okay. All right. So now this is what we have performed. Okay. And it looks quite okay. Okay. it is not that it is perfect. It is not perfect, okay? You can see some flashing here, okay? But on the other hand, okay, what makes this work perhaps a little bit special compared with other existing denoising work is that I think we all learned in university when we were in school that to do denoising, a very simple way to do it is to just run a low-pass filter. I mean, it's easy, right? Because noise by nature is high frequency in nature, okay? Usually uncorrelated and stuff like that. Using low-pass filter, you'll be able to remove quite some noise, okay? The problem of low-pass filter is that very often the edges will become blurred, okay? And that is undesirable, okay? You'll be talking about the difference between a cheap VCD versus a high-quality DVD, right? Or a regular DVD versus HD, right? Something blurred and something sharp. That makes a big difference, okay? People expect something sharp, especially when people are paying for it, okay? And so as a result, it is important that when we do denoising, we are maintaining the edge integrity at the same time. We are preserving the edge sharpness at the same time. And this is our goal in our work, that we try to do denoising while preserving the edge sharpness, okay? So this is our goal, okay? You notice earlier on, if I can show this again, okay, the first frame looks pretty bad, okay? Now what happened is that because our method turns out to be a temporal domain method, so the first frame is pretty bad actually, okay? You basically have nothing in the past to help you. So the first frame is pretty bad, but if you go to the next frame, it goes better. Next frame, it goes better. It goes better, okay? And then it basically becomes quite okay, all right? So going back to the beginning, just play, okay? It will be quite okay. Okay, and notice that the edges are quite sharp. Notice that, okay? Edges are quite sharp, and this is our goal. We want the edges to be sharp, okay? So that is what we're trying to do, okay? Yes?
What if you showed a sequence with high temporal motion?
Good question. Good question. Okay, right. Now, what we're going to show is a class of temporal filtering, right? Okay, and one prerequisite is that we want to establish correspondence between the current frame and the previous frames, okay? Something here also happening in the previous frame and happening in the previous frame, okay? So what his question is saying is that what if the object is moving so fast that you cannot find, when you find something here, you cannot find something in the past, right? That's the question, right? Okay, the answer is, unfortunately, in this case, then you cannot work so well, okay? Which means basically that you will need to combine this method perhaps with some spatial method. Okay, because what I'm saying is this method is limited by, well, this method has a basic assumption that we can establish correspondence between current frame and the previous frame. Now, this method by itself is not going to die just like that, okay? Basically, what this method would do is that when it detects that the correspondence between the current frame and the previous frame is low, when the similarity is low, then basically it's going to take a weighted average between the current frame and the previous frames, okay? Well, when it detects that the previous frame doesn't look like the current frame, it's going to put a big weight on the current frame. Basically, that would mean that you have very little denoising effect. It's not going to damage the video too bad, but it's going to have locally noisy effect.
When you say correspondence, it reminds me that earlier you said if you encode this clip, motion vector is going to go crazy. That means you can't get a good correspondence, right? So there's some, I'm sure you're going to come to that, but it seems to me there's a little bit of chicken and egg problem.
Okay. Yes, okay. This is exactly why in our simulation we don't use fast algorithms. Because fast algorithms make assumptions. We are actually an expert in doing fast motion estimations. We have some method that went into the standard, MPEG-4 standard, okay? But on the other hand, we realize that in those fast algorithms, we make assumptions which may not be true in noisy video. And so as a result, we resort to full search, okay? When you do full search, actually, it is not too bad. It is not too bad. When you actually have correspondence, but it's disturbed by noise, you basically would be able to find it. You basically would be able to find it. It's just slow. Okay? But later on, I'm going to talk about a method to make it fast. That's one thing. Okay? But if unfortunately, if the motion is really going so fast, you're doing rotation, crazy motion, okay, the eyes blinking and stuff like that, then there's nothing you can do. Okay? And the method will basically fall back into doing very little denoising. Okay? So locally, you may have some region which has a bit more noise. This is our method. Yeah.
There are any drop frames, also the quality will degrade and then could go up again of the denoiser. So if there are drop frames between the camera and the encoder, you start losing the motion that comes from...
Did you say drop frames?
Drop frames, yes.
When you drop frames, it doesn't mean you have bad motion or good motion, it's just you just drop frames.
It's like high motion now.
Oh, high motion, oh, okay, when you're in demanding situation, okay.
1 to 10, and you drop, say, between 3 and 6. Now
Okay,
you drop,
sure.
you don't have this information. Then
correct,
I would expect
okay.
the quality of the denoiser to go down. Then when the frames come in, and wouldn't this be irritating to the human eye? That's one question.
Yes.
And the second thing is the interlacing. What do you do with it?
Oh, wow, cool, interesting. Okay, all right, sure. First question.
I think this is encoder technology.
So,
I mean,
so
drop
for
all the
interlace
frames.
contents, what are you going to do? Are you going to start after the interlace?
Okay, all right. I'll handle one problem at a time, one question at a time. Right. What's the first question again?
With drop frames.
Drop frame, yes, okay. All right. For drop frames, okay, you're in fast motion situation, okay. Basically, what that would mean that we're going to fall back to his problem. Basically, when you cannot establish correspondence between current frame and the previous frame, so this method will not work very well. And you need to rely on some spatial methods to do it, okay. But there are some existing spatial methods that can do reasonably well, actually. Right. But one beauty, at least for that particular situation you mentioned, is that when motion moves fast, your eye cannot see very well. So actually, if you blur it a little bit, it doesn't matter. So actually, I would tend to use spatial methods to blur it, because keeping the edges sharp is not the top priority when the motions are fast. Right. So I wouldn't worry about that too much. Okay. So basically, this method is really should be designed for, has to work with spatial methods. What I'm saying is, when I'm filming, looking at you, and all of a sudden I change to another scene change, when you do scene change, this method would not work at all, because you don't have history, right? So you don't have anything in the past that can help you. So this method actually has to work with spatial methods. Yeah, so.
Interlace contents.
For interlaced content, okay. Oh, before I talk about that, one thing I do want to mention, we've certainly looked at spatial methods, and one problem about spatial methods is that the complexity is very high. Number one, every single pixel, there are so many pixels in the frame, and every pixel, suppose you just do a 3x3 low-pass filter, stupid low-pass filter. It turns out that the complexity will be so high, okay, if you use a larger filter, okay, there'll be so many operations you need to perform, and spatial methods are just so slow. Okay. The beauty of this method is that we only do a few operations. We're actually, you know what? We're only averaging not 9 numbers or 5x5, 25 numbers. We are not doing a weighted average of 25 numbers. We are taking weighted average of 3 numbers, 4 numbers. That's it. The current frame and the previous frame and maybe the previous, and just that's it. That's all. We're just taking weighted average of 3 or 4 numbers. So complexity-wise, it's quite simple. When it comes to the filtering operation, motion estimation by itself is very slow. Okay, so that's why later on I'm going to talk about a fast method to do it. Okay, this method is basically a pre-filtering technique, meaning that before you compress, we assume, independent of the codec, you are going to do some pre-filtering, denoising. Okay, and so as a result, if you want to do the motion estimation by yourself, it's going to cost you a lot of computation. Okay, so, but yeah, before I should answer the second question. You talk about the interlacing. Okay, I don't understand the question. The interlacing versus denoising, what's the...
Interlaced contents.
Yes.
So when you have field n and then field n plus 1, and there is that toggling between the lines,
Yes.
would this affect also the quality of your motion of your denoiser or not, before going into the encoder?
I don't think it's going to be a problem. I think it will work. Because the same problem happened to frame and field. I don't see field coding being more difficult than frame coding. It should be quite similar.
So you didn't try the interlaced contents?
But
the question is that toggling could sometimes deviate away what you call the registration, figuring out where things are
right.
from time t to t minus 1 to t minus 2.
Yes.
But it depends on the method. Some of them, maybe this one would work fine, as you said. I don't know. So
We'll see.
we'll see.
Yeah, later on, in the second part of the talk, I'll talk about some robust motion estimation. Perhaps that can address this issue. Basically, we understand that in noisy situation, motion estimation is just hard. How can you make it robust? How do you make it trustworthy? And hopefully make it fast as well. So we do have a certain way to do it that can kind of at least partly solve the problem.
I may be getting ahead, but so in your work, do you assume that noise is white Gaussian noise? Or because the reason why I'm asking is that the camera has a nonlinear response, and so noise is actually not white Gaussian noise.
Okay.
So if you make that assumption, then whatever denoiser that you have is going to be non-optimal.
Okay, right, sure. We use white Gaussian noise in our simulation, but I don't think we need to make that assumption that it is white Gaussian. It doesn't need to be. In the formulation, we don't need it to be white Gaussian. No, there's no need to be white Gaussian. Mm-hmm. Right, so the method should work for other situations too. Right, okay. All right, so maybe it's time for us to go back to the PowerPoint and see what we do. Okay, all right, full screen. Okay, right. All right, so motivation again, I think we've talked about a lot of motivation already. Okay, video quality, okay, when you have noise, okay, noise is going to corrupt the video, making it look bad, okay. And actually, especially when you're in a high bit rate situation, DVD, HD coding kind of thing, because of very high bit rate, noise actually can survive compression. Noise can survive, okay. So as a result, somebody needs to take care of the noise somewhere. Okay, so denoising is a way to handle that. Okay, and not only that, with the presence of noise, it is going to cause bits to represent, and so it is going to make the file bigger. If you denoise it, it is a quite good chance that you can make the file smaller. Okay, and so actually there are situations in which sometimes, even if the video is not very noisy, you still want to apply denoising, because you want to apply this as a means to reduce the file size. Okay, you do it maybe not to do denoising, but rather to make the file small. In other words, you are intentionally using denoising to remove some image detail so that your file can be smaller. You know what I'm saying? So denoising is another way to achieve a smaller file size. So this is kind of interesting. Okay, and okay, because of the presence of noise, very often the motion estimation is going to have trouble stopping. Okay, and so as a result, the presence of noise actually will make your encoder slower, more complex, more things to compute. And not only that, because with the presence of noise, okay, your motion estimation, no matter what you do, is not going to do very well. Okay, so the residue is going to contain a lot of energy. And so as a result, you need to spend so much more complexity to encode all these non-zero DCT coefficients. Okay, so actually in our experiment, we realized, to our surprise, that denoising not only can make the file smaller, it can make your encoder faster also. Just simply doing denoising. So it's kind of interesting. Okay, so this is quite a cool thing to apply to your codec. All right, so it's kind of fun. So, okay, in this example, we have compressed the Foreman sequence. Okay, we have add noise to Foreman, okay, and then try to compress it, okay. And number one, with denoising, the file can be quite a bit smaller. Okay. Number two, the compression time actually is much faster, can be faster. All right. Now this is a little bit extreme. Of course, this is we're doing all the favorable conditions to make sure we work well. Okay. But this gives you the idea. Using denoising, you can make the file size smaller, and also you can make your coding faster. All right. So that's an advantage. Yes.
So you basically like losing some quality when doing that.
Yes. Mm-hmm. Yes, what we are doing here is, well, you need to understand, if you have an input video, if you treat the input video as holy, you cannot touch anything. If you treat it like that, then yes, we are causing distortion. But remember, we are doing denoising. We are actually changing the input. Okay, we are saying that no, the input is not holy. The input is actually noisy. There is something undesirable inside. I'm going to make it better, while at the same time making the file smaller, making everything faster. Right, so this is a little bit different. But on the other hand, you are right. Actually, we are indeed losing a little bit of the detail. And so as a result, we may have some problem. For example, if you look at Foreman, okay, if you are familiar with the Foreman sequence, okay, there is quite a bit of dots on the wall. Okay, you will notice if you compare this with the original, that some of the dots are gone. Some of the dots are gone. Okay, now so this is a price you're going to pay. Okay, yes, you're going to lose a bit of the detail. But certainly for the big edges and so on, you are not going to lose that. But for small, fine details, you may lose that. Okay, for example, if you look at me, maybe I got all these dots because of my beard, whatever. Okay, after you do denoising, maybe you look nicer. Now, is that good or bad? I don't know. Sometimes, you know, if you're looking at ugly Betty or something, okay, sometimes the director wants a person to look ugly. Okay, and now you make them pretty. That may not be so good. Right? Sometimes there may be detail that the director wants to keep in the content. Right? So in that case, you want to keep that. If you fail to keep that, you're not doing the right thing. Okay, and so as a result, it depends. But yes, indeed, you are going to pay a price for that. Yes, you're right. Okay.
Make sure that I understand here. So the 50% coding time reduction here, is it tied to the motion estimation? The fact
Two
that
things: motion estimation and VLC.
Yes.
And VLC too.
So that means that in this particular experiment, the criteria using for motion estimation is that you need to reach a certain level of upper bound for what the distortion can be between two blocks, right, when the reference frame and the frame. And once you achieve that, you stop the motion estimation. So filtering helps you basically achieve that threshold area. Is that the main gain of
Okay, right. Now, this number may be a little bit misleading because in your codec, when you have a codec, you may not be using full search. But here in this example, we are using full search. We are using full search, stupid full search, brute force full search. And so as a result, you can increase it, you can gain so much in the coding time. Because if you already are using fast search, how can you gain? You can gain so much.
But you stop once you achieve a certain threshold.
No, full search is full search. Full search, you check everything. Yes, right. There's no early termination criteria over there. Well, we basically find out that early termination can get you into the wrong decision because of the noise. So that's why we don't do early termination. Yeah. Mm-hmm. So it is sensitive to noise, early termination strategies. Mm-hmm. Another question?
Do you assume that there are no compression artifacts in the original video? And because you know, when you capture a video, typically it has been compressed. Nobody actually can. Yeah.
Oh, I see.
So if the original video, which is noisy, has compression artifacts, will your algorithm actually reduce that?
Okay. We didn't do experiment on that. Okay. We assume the video is original with noise. Okay. If you have coding artifact, I think to a certain extent we should be able to suppress it a little bit. Okay. But then the assumption is a little bit different because the noise is no longer so independent. The noise is more systematic. And I am not sure. I'm not sure how good it will be. I think we need to do some experiment on that to try out. But I would guess that you will be able to suppress it somehow. Right. Right. So that's my guess. Mm-hmm. Okay. So we'll continue. Okay. So temporal denoising. Okay. All right. So the method we use is called a multi-hypothesis motion compensated filtering. Okay. We utilize multiple pixels along the motion trajectory and basically do a linear combination of them to find the best, best estimate. And what we are doing is actually an optimal solution. We are doing a linear minimum mean square error estimate. Okay, so it is you can then trust that it should work pretty well. Okay, because it's an optimal solution. Okay, so let's see. Okay, P2, P1, P0. Okay, all right. So what we are saying here is that suppose this is a current frame. Okay, there's a certain region noisy. Okay, if you can manage to find in the previous frame something corresponding and something corresponding, and what we're talking about is basically take a weighted average between this one, and this one, weighted average. Okay, of course, in the weighted average situation, the coefficient is important. The coefficient is important, right? And so basically, we use LMMSE to determine the coefficient, right? To find the best coefficient for that particular situation. Okay, all right. So this page looks a little bit, lots of equations. Okay, basically what we are saying is that we want the denoised version to be equal to something plus a DC. D is a DC. Okay, here W is the weight, O is the observation. Okay, now O contains Fn and then P1, P2. Okay, Fn is the current frame. Fn is the current frame. P1 is the T minus 1, frame T minus 1. P2 is frame T minus 2, and so on. So here in this example, we are talking about M frames. Okay, current pixel, and then the previous few pixels. Here we already assume that we have performed motion estimation. You find the corresponding motion. You find the corresponding matched location. Okay. So what we are saying is that for every of these guys, you're going to weight it by a certain number W. So this is just a simple weighted average of the past few numbers. Okay. Now, mind you, when we usually assume that noise is kind of temporally stationary, meaning that the noise variance tends to be stationary over time. But here we do not assume. We allow individual P1, P2 to have different variance, different noise variance, because while we need to take the noise variance into account, we also need to take into account the motion mismatch, just like what you said earlier on. When the current frame and the previous frame, when the motion estimation cannot do so well, you have a mismatch, right? So that mismatch is not due to the noise. That mismatch is actually due to the motion mismatch and so on. And so as a result, we're going to take that motion mismatch into account and put that into the variance of P1 or P2 and so on. All right? So there may be a situation in which P1 you can find a good match, so the variance of this will be pretty small. Okay? But for P2, maybe motion estimation doesn't work very well. In that case, P2 may have a large variance. Okay? So in this case, with this formulation, then we will smartly allocate more weight to the guy with smaller variance. Right? So that's what LMMSE does. So that this method works quite well. Okay? So what we minimize is that we want to minimize the expected value between the denoised version and the original value. Okay, we want to minimize this one. Okay, and the solution is the standard LMMSE solution. Okay, covariance matrix U thing. Okay, 1 over that, and so on. Okay, this is the standard thing. I mean, if you open a textbook, you'll find it. So this, I did not put a lot of detail here because this is the standard solution. Okay, and it is not hard to find. Okay, so this is the solution, and basically in here, U is the so-called prediction error vector, which is basically in the current frame corresponding to Fn. The error vector is basically the noisy observation minus the original. So actually, this is just the noise. Whereas U1, U2, and so on, U1, U2, and so on are the temporal prediction error as well. Okay, so yeah, so this is that solution. Okay, and then the mean square error of the temporal denoising is equal to this. Okay, with this solution, it is well known that you can estimate the mean square error, and that is equal to this expression. Okay, in the special case that all these guys are independent, then basically this term would mean that this is basically sigma 1 square plus sigma 2 square plus sigma 3 square, so something like that. Okay, yeah.
You have to know the noise, the original.
We need to estimate. We actually, for this method, we need to estimate the noise variance. We need to estimate the noise variance.
That's all you need. Just the variance of the noise.
Yes, we need the noise variance. Yes. We also need to, not only the noise variance, but also we need to estimate the noise variance due to the motion mismatch. So basically what we do is we still do block-based motion estimation. Okay, and basically with that, then you can calculate the mean square error between the current block and the predictor block. And basically we use that to estimate the mismatch variance.
But the noise is per pixel noise, right? It's not constant.
Per pixel.
Per pixel, so the noise can vary.
Well, when we do the simulation, it is white noise, white Gaussian noise with fixed variance throughout the whole sequence. When we do the simulation, we do this, right?
Right. That's why I asked that question, because in reality, that's not true.
Okay. Yes.
Because of the camera nonlinearity, the amount of noise is a function of the brightness itself.
Oh, is it?
Yes.
Okay. So brighter region has less noise or more noise?
Sorry?
Brighter region has more noise or less noise?
No, not necessarily. It actually goes like up and down, like a little hump.
Okay.
But yeah, that's the reason why. Because if you make the assumption the noise is constant, then this is not optimal.
You're right. Yes. We did not assume noise is constant, but in our noise parameter estimation, we do assume noise is constant when we estimate the parameter. This model doesn't require the noise to be constant. Or maybe it does. Yes, sorry, it does. Yes. Right. So, but good point, yes. Perhaps you can make it better by dividing a video into a smaller region and locally estimate something. Perhaps that would be a little bit better.
So what do you go about estimating the noise power again?
Noise power?
Yeah.
Mm-hmm.
Since you have,
Okay, right. What we do is that we look at the video and we assume that the video frame contains some part which has high frequency but some part which has low frequency, which is smooth. Right? And basically, when you look at the smooth region, the variance should be almost zero. And if there's any variance, it would be due to noise. Okay, so basically, we look at the locally small regions. Every region, we look at the variance, and we look at the minimum, the last smallest 3% or something, and take the average of those things as the estimate of the noise variance.
You're doing it in a spatial domain as opposed to the temporal domain.
Yes, we use spatial domain stuff to do it. Right. Mm-hmm. Yeah. Okay. Okay. Now, when we do this, we have a choice. Okay, we can choose to do this temporal filtering in a recursive manner or a non-recursive manner, meaning that suppose you have denoise frame or the previous frame already. Now you're trying to denoise the current frame. Okay. Well, now we want to use time t-1, t-2, and so on, right, to help you. The question is, are we going to use the original noisy video to help you? Or are we going to use the denoise video to help you? The effect is going to be different, right? If you use the original noisy video, this is not recursive, okay? But if you use the denoise one, then this is recursive, okay? And we find out that if you use the recursive, the effect actually is much better. And so it is the reason why when we average only 3 number or 4 number and get very good result has a lot to do with this recursive filter, okay? Because the previous few frames has been so much denoise already that when you compare with the current frame, you tend to put a big weight onto the previous frames so that you have a very big denoising effect. Whereas if you consider spatial filtering, even the 3x3 very small filter, you cannot denoise very much. Because every one of them has so much noise. But in the recursive situation, the previous guys have been so much denoise that actually you can have very good denoising effect, even with just 3 or 4 numbers, averaged together. So.
When you do recursive, you face the danger of oversmoothing.
Yes. Yes.
That was my question on the previous slide. Those previous frames you were referencing, so those were the original sources or the denoise sources?
Okay.
Which were they? Were they the denoise?
In my simulation?
Yeah, in your equation on the
P1,
slide.
P2, P3.
Yeah, P1,
Okay.
P2. Are those denoised frames or originally noisy frames?
It can apply to both. The formulation can apply to both.
Which ones do you use?
We
better
use
performance?
we use the recursive.
The noise one, so that's why you get the loss of sharp.
So
And
we
motion,
will.
If you look at it, it looks like the FIR predictor, but I guess you can. And essentially, you're doing IR filter along the motion trajectory. So.
Yeah. So effectively, we're not doing IR. I think we're doing IR. Correct. Yes.
What is the effective tail downs then? I mean, it could be 3, 4 numbers multiplied, but the effective tail downs of the filter can be quite long, right? Yeah.
Yes. I did not take a look very closely into that. Yes. But yes.
Exactly. But I think the trick is that noise estimate is tricky because it also has motion mismatch noise in there as are combined. So
Well, the noise parameter estimation is done in the spatial per frame, so we don't need to worry about the motion mismatch for that. Mm-hmm. Right. Okay. So anyway, yeah. So anyway, when the variance goes down, that means the mean square will go down. So anyhow, so this method works quite reasonably well. Okay, that's about it. Okay, to give you an idea of the simulation. Okay, all right. Now this is a mobile sequence, performance sequence, new sequence. Okay, you can use only 0 frame, which means no denoising. Okay, you use 1 frame, so that means you average 2 guys. Okay, m equal to 2, 3. Okay, all right. With no denoising, this is the PSNR you get. Okay, no denoising. Okay, all right. Using 1 guy, you can increase it from 22 to 25 dB. Okay, 1 more, you can go from 25 to 26, and then 26 to 26 again. Okay, you see that the major gain comes from 1 guy. Okay, 2 guy, you gain a little bit more. 3 guy, you a little bit more. Doing further is not going to give you a lot of gain. Okay, so that's why from our simulation, we tend to believe that you get the maximum benefit out of either 2 or 3. I tend to use 2 myself, right? But it depends. Yeah. Okay, complexity, of course, when you go from 1 to 2 to 3, complexity is going to increase linearly as well because of the motion estimation. Okay.
What was the frame rate on these sequences?
30 frames per second?
30.
Full rate, yeah. Right. Something like that. So, okay, some example. Okay, so this is a noisy video. This is a denoise video with m equal to 2. So that means 1, t minus 1, and t minus 2. That's it. Okay, and you can do quite well, actually. All right. And, yeah, this is quite a bit clean up. Okay, and this part can still be quite good. Okay. When we have good motion correspondence, this method actually works quite well. This method actually works quite well. Okay, all right. So, okay, another example. This is a flower garden. Okay, and the original noisy video m equal to 2, and this is what you get. Okay, the sky looks clean, and you still see some textures here, so quite reasonable. Okay, you do see around here there's some noise, right? Yeah, you do see some noise here. Okay. Now, when you locally, when the motion mismatch, when you have motion mismatch, this is the kind of effect you're going to see in this method. Okay. Here, motion estimation is doing well. Okay, you clean it up. But here, locally, motion estimation doesn't work too well. So in that case, you're going to see some locally, some residual noise there. Okay. So basically, I think around the house, rooftop, you see some noisy patches here and there. And this is a place where motion doesn't work so well. And so we don't do so well.
What's somewhat troublesome to me than the residual noise on that hole there? You actually have a place where it seems to me that you actually got too strong a weight from the wrong frame. So there's like a geometric distortion.
I'm sorry, I missed the question.
So the question is why around the pole there you're missing the noise so badly compared to other regions where you did much better job?
Why is it so bad? Well, basically, any place where the motion estimation doesn't do so well, you're going to have that kind of effect.
Yes, of course. So, for example, if you actually copy on your model, if the frame that you're getting the motion, the average form, if that frame is denoised, then it might have a much higher weight than the current frame. So the key danger is that you get the wrong block, essentially. So you get blocked from the order. And that's what seems to me to have happened with the pole there. So there's a place in the pole.
Right, the pole in the middle, right? Not the white pole or the...
That pole
right here? Right there.
Okay.
Yeah.
Where there's that
chunk out.
Yes.
Okay, all right. If you ask particularly why this thing is happening, I'm not very sure. Okay, I'm just pointing out to you that, yes, this will happen whenever the motion doesn't work too well, this will happen. When you're talking about this sequence specific, why this is happening here, right?
I'm asking how often does it happen?
How often it happens? How often it happens? Well, basically when motion doesn't work so well, that's it will happen. I mean, that's how often does motion work well or not well? So that same question. It's actually the same question. Yeah, it's a sequence dependent, right? And here we are assuming a translational motion, right? If you change the model, allow yourself to have smaller blocks, allow yourself to have rotational motion and stuff like that, you can do better, right? But on the other hand, we...
Because that happens, in this frame it happens twice already, right? So on the same pole down there, you have the same effect. And then when you actually, even though this is true.
You're talking about here, right?
No,
and there's one further down.
By the gate.
You mean here?
No, the same pole.
same pole.
Same pole, here.
Going down.
Yes.
Here.
Yeah.
And both basic motion has mismatch, and the pole and the background gets average.
Well, the problem with these spanning sequences is that our eye actually track the objects.
Yes.
So if you don't do a good job, and then you're going to see a lot of flickering.
Yes.
True.
true. To solve the problem, okay, to solve the problem is actually not very difficult. Okay, to solve the problem, you need to combine this with spatial method. The idea is quite simple. When this method works well, you use this method because this is actually better than spatial method. But on the other hand, when this method doesn't work well, you need to put a bigger weight onto the spatial method. In other words, you want to actually do a linear combination between the temporal prediction, a temporal denoise version, versus a spatial denoise version. Take a weighted average between them. When this method works well, you trust this guy, give this guy a big weight. When this method doesn't work well, you give the weight to the other guy. Do you know what I'm saying?
The complexity on the spatial
Yes. Yes. Later on, you're going to see when we look at the spatial the robust motion estimation, we are actually going to do spatial denoising as well. We're actually going to do a spatial denoising, and we're going to combine that with this one because anyhow we do it over there already for the motion estimation. We may as well use it. So we use that. If we combine that one with this one, then you're going to get a better result.
So in this particular circumstance, this frame,
yes.
Do you know is the motion actually is translational or is there any rotation here?
I don't remember. Well, this is obviously panning like that, right? But I think the things are becoming a little bit bigger over time. I think.
I'll assume that when you do motion estimation, you just use the translation lines. So what the blocks are vertical. You don't do rotation blocks.
No, we don't do rotation. We're just doing regular motion estimation.
The pole is it's not straight. So maybe that's what's happening where the corner gets cut off. I wonder like if the motion is, if there's some rotation here, then that can happen through.
I don't exactly remember this sequence. I think this sequence is filmed by probably a car driving along the street, something like that. And so as a result, there's a scale change here. You don't have just plain simple translational motion. The things are becoming smaller and smaller. Okay, and so on. So motion estimation has some problem in here.
What's the block size that you're using for your motion estimation?
I think we use 16 by 16. Yeah, just regular.
So for all pixels in the 16 by 16 block, you assume the same corresponding pixel, right? So maybe around
same motion vector.
Same motion vector. So maybe it may be a very good estimate for say the center pixels, but then on the edge, maybe the correspondence is not so strong. Because you're forced to use one motion vector for this whole.
Possible. Yes.
Because I didn't notice anything that would suggest that, but just wondering if you have any.
This particular example doesn't show, but there are examples in which you see a noisy pattern which are blocky. And this is due to our block-based motion estimation. Yes. Okay, all right. So noise robust motion estimation. So here we're addressing that issue now. Okay, when you do motion estimation, okay, the presence of noise causes you a lot of trouble. Okay, for some situation, okay, when you have noise-free situation, when you have no noise, you may have a pretty nice residual surface, right? Error surface. Okay, the presence of noise is going to cause this to become very fluctuating, okay, noise-like. Okay, so then this thing is noise-like. And unfortunately, many of the fast motion estimation methods assume some kind of gradient descent, greedy algorithm, okay? And we are going to fail, and that method will fail pretty badly in this kind of situation, right? When the error surface goes crazy, okay? And the early termination can cause problem too, okay? Sometimes you can be easily trapped in here, sometimes good, sometimes bad, okay? You think it's good enough, but actually it may not be so good after all. Right. So as a result, we find out that in noisy situation, it's just hard to do motion estimation. Early termination strategies has problem. Greedy local search thing is going to have problem, and things like that. Okay, and this will greatly increase the motion estimation complexity and also reduce the accuracy as well. Okay, and so as a result, what we propose to do, what we do is that we propose to do two things. Okay, we apply a filter first. We apply an urge-preserving low-pass filter, okay, and then we do fast noise robust motion estimation. Without this one, we cannot do fast algorithm, and we would do full search. So that makes it very slow. Full search is very slow. After applying this one, then actually we find out that it is now not so bad to do fast algorithm. After you apply low-pass filter, then you do it, then you can do quite a bit better, okay? And after that, we just do the regular denoising stuff, okay? Because the edge is important. Because the edge is important. Why not? No, edge is very important. Edge will determine whether your motion is going to be correct or not, right?
Noise also gives the edges because of the false edges.
I think he's trying to say is that as soon as you apply a certain filter, spatial filter to the video, as long as it's consistent in the way it affects the video, the matching is preserved, regardless of whether our edges are
No,
sharp or
because you
smooth.
could just do a low pass filtering and then the resolution decreases. So
not matching.
So then when you do the match, you can't resolve to within that resolution. So if you preserve the high frequencies of the edges, you can actually get it to something that's not.
That's basically your matching edges. Gives you the best information.
If you recall, one of the goals we have is that we want to preserve edge sharpness after you do the denoising. Then the edge precision is actually quite important. If you low pass it, then the location of the edge is not so precise. When you
low pass filter already is not real time, and now you can edge preserving low pass filter, trying to correct the motion to compensation.
Okay, yes.
What's the balance there? Do you really
What is
get
what?
a speed up?
I'm sorry, I missed that.
Do you really get a speed up?
Yes. Yeah, I'm going to show you. Yes. Well, we got to speed up compared with full search. Okay. Yeah. Well, we can go a little bit further down to look at the results. The number of search locations. This is full search. Our method. This is the speed up we're talking about. We are getting this one give you about 50 times speed up, 50, 60 times speed up. This one give you, I don't know, close to 100 times speed up. Okay, about what? 100 times speed up. Okay. Computational complexity, number of search location. Computational complexity. This is the regular method, full search. This is our method. And number of addition is this many, so I don't know, 20 times. Number of addition, we need to do a little bit more multiplication. So we do a little bit more multiplication, but not very much. Okay, so yeah, so we managed to reduce the complexity quite a bit. The speed up, processing speed for CIF, okay, the original method, we can only process on our P4, 3.2 gigahertz, 1 gig RAM, Windows XP platform, we run it. The original method, using full search, we can only do 2 frames per second, 3 frames per second. Using the fast search, we can do 28 frames per second, 20 something per second. Right, so this is quite a bit of speed up, Okay, the motion field becomes smoother. And also the quality will become better too. Okay, this is noisy. This is the original method. This is the fast method. The fast method actually can give you, well, okay, in this case, similar PSNR. Sometimes you can get better PSNR. Okay, believe it or not, we're using fast method, but we can get better PSNR. So it's kind of funny.
What is the filter that you got from EPLF? What is that filter?
Yes, I'm going to go back to that. Yes. Okay. We like that filter. Yeah. Right. In this example, okay, this is Sean sequence, the noisy video. Okay, with no. Okay, I think this is the amount of noise. 3 different situations. This is not so much noise, bigger noise, so that the PSNR is smaller. Okay, and M equal to 1, 2, 3. 3 different situations, and the original method. This is the fast method. You can see that the fast method has a little bit of gain over the previous method, but in some case we can actually gain quite a bit. All right, so it's kind of interesting. Okay, the most important thing is you don't lose. You don't need to lose the PSNR when you use this method. So, kind of interesting. Okay, all right, I'll go back and look at the thing, what we do. Okay. Okay, all right. Okay, this is the filter we use. This is the filter we use. We look at a 3x3 window. It's a very small filter. It's not a big filter. It's a small filter. Okay. We like this filter. We use it quite many times. This used to be our spatial domain low pass filter, denoising filter actually. We used to use this for denoising filter. We used to use this for even inverse half toning. If you know half tone data, very noisy, this method actually can suppress that quite a bit. So kind of interesting. Okay. Now, the equation, my student write this equation very poorly, so it's very hard to see. Okay. But basically, this is a 3x3 neighborhood. Consider a 3x3 neighborhood. There are 9 numbers. Okay. We're going to take a weighted average of the 9 numbers. That's all. Okay, but how do we determine the weight? Okay, now especially we are talking about edge preserving. Very often when you do edge preserving, you need to do some kind of edge detection and then do directional filter along the edge, right? That's one way to do it. But we don't want to do that because that is going to incur a lot of complexity, very troublesome. Okay, or if you want to do median filtering, it would preserve edge also, but then you need to do sorting and stuff like that, which is bad. This method doesn't do sorting. This method is a simple 3x3 weighted average thing. Okay, the beauty is really in how you determine the weight. This method is actually quite interesting. The weight now here, imagine this thing as the 9 numbers within this neighborhood, 3x3 neighborhood. Okay, each one of them is weighted by a certain number. Okay, well that number is add up to 1. Right, as expected. Okay, basically this number is proportional to something complicated. Okay, basically this equation is not very, very clear. Okay, what you want here is that suppose you have a target value within a certain neighborhood. Suppose you have something called a target value. Okay, and if you're close to that value, this guy is trustworthy, and you're going to give a big weight to that guy. If you're very far away from the target value, then we give a small weight. Okay. In a sense, this method allows us to suppress outliers, basically, without doing edge detection. If you can do edge detection, if you know that you're on this side of the edge, and you forget about those other guys, right? You only take this side and take the weighted average, then you will have no problem. You'll be able to preserve the edges. Right? Within the neighborhood, if you know there's an object here, something on this side, something on that side. If you decide the weighted average between these values and those values, you're going to have a very bad value. Because those values has nothing to do with you and you try to weighted average, those guys are outliers and it can badly affect your results. The basic idea here is I want to forget about those guys. I only use the guys that are trustworthy and just weighted average them. Okay? Basically, that's the idea.
Bilateral filter.
Huh?
It's basically a bilateral filter.
Bilateral filter?
Well, in the computer vision and computer graphics community, we call this a bilateral filter, where you basically look at the spatial and the extent. In other words, you're trying to filter locally. You look at not only where it is, but how different it is from the intensity, so that you downweight any pixels that's far away.
Yes, that's the idea. Yes, that's exactly the idea. Exactly the idea. Mm-hmm. Yeah, so we're doing that. Okay, so this filter is a little bit more complicated than a regular 3x3 low-pass filter, okay, because we do need to do a multiplication. That weight is important, okay. But on the other hand, it is not so bad. It is relatively simple compared to a lot of other methods. Okay, so we like this method a lot. Okay, so it actually works quite well. Okay. So for example, if you look at this example, okay, this is the original video, this is the noisy video. If you apply our filter, this is what you're going to get. So as I told you, this method by itself actually is a denoising filter. It is a denoising filter. But the beauty of it is that you can preserve the edges. If you look at this edge is very, very sharp. Okay, this is what I'm talking about. This filter can preserve sharp edges. But for the thin edges, it does not preserve it. But for sharp edges, yes, it will preserve it. Okay, all right. So yeah, so these are actually pretty sharp. Okay, so this is a pretty good edge preserving filter. So it's kind of nice. Okay, all right. So after applying the edge preserving filter, okay, now you got something which is quite good. All right. Now we are going to use this to perform our motion estimation. We're going to use this. We don't want to use this one. We want to use that one to do motion estimation. But later on, when we obtain the motion vector, we will still use the noisy one. We will still use the noisy one to do the denoising. In other words, at this point, we are only using this guy to do the motion estimation, but we will not use this for the denoising. Okay? We will use the original noisy one to do the denoising. Because we do understand that this method will suppress some of the details. It actually will suppress some of the image detail. All right? Yeah, so we cannot fully trust it. Okay? But for motion estimation, this is good enough. Motion estimation, this is good enough. And not only that, as I mentioned earlier on, in the case when the temporal denoising doesn't work, we actually have the option to do a weighted average between that guy and this one. Because this one actually doesn't look too bad. This actually doesn't look too bad. It's just you just lose some detail. Okay. When temporal denoising doesn't work, it's better than nothing. All right. So actually, take a weighted average between this one and the temporal denoising. Works quite well. Okay. All right. So here, this is the second stage of the motion estimation. So what we do is that we consider three motion vector predictors. Okay. The first one is a median filter. Median predictor, okay, meaning that if this is a current block, you have the block on the left, on the top, on the left, upper left, okay, and they already have motion vectors, and we treat them as likely predictor. Since they're so close, it's quite likely that the motion vector of this guy is similar to the neighbors. So we take the median of them, okay, and treat this as a median predictor for the current block. Okay, all right. We also look at if this is a current frame, this is a previous frame. If you look at the co-located block, the previous frame also has a motion vector. Given that in the real world, a lot of the things don't move so fast, so the co-located block, the motion vector of that guy, perhaps is a good predictor of the current block motion vector as well. So that is another predictor. Okay, and then there's also another thing called temporal predictor, meaning that we usually, remember, we are going to do, if this is a current frame, this is t-1, t-2, t-3. When you do t-1, okay, you do whatever motion estimation. But when you do t-2, you already have a motion vector for t-1, and it makes sense for us to just double it and use that as a predictor for t-2. And so this is the temporal predictor we're talking about. Okay, and so you scale the pass motion vector according to the temporal distance as a predictor. Okay, so this is three predictor we use. Okay.
Sorry to ask, but how, from your experience here, how sensitive those methods are to resolution? If I start with a set video, this is fairly coarse detail, but as I go increasing, going to the HD kind of resolutions, clearly the video becomes oversampled, especially in the spatial domain. Is there some provisions you typically like to incorporate in the way you define the kernels, depending on the resolutions?
Okay. No, there's no particular provision. But one thing I can comment is that these are predictors, and predictors work well at small resolution. Predictors don't work so well in HD, in large resolution. They don't. Okay. So I do a lot of work on fast motion estimation, and we noticed that when you have small resolution video, very often, just as long as you examine the predictor, you're already done. It happens quite often. Okay, but in HD kind of situation, the predictor are not so accurate, and almost always you need to rely on some kind of local search to find the optimal location. Yeah, so local search is very important in HD, not so important in the small resolution.
You change the strength of the filtering according to the target video quality, because when the video is coded as high quality, probably you don't want to denoise a lot. But the video is coded as low quality, you can denoise a lot.
Okay.
But still doesn't hurt the video quality.
Okay, sure.
So here you only apply some constant strength for the filtering.
Okay. We don't adjust it. We also did not do a lot of simulation on the HD kind of thing. We actually did it in low resolution, so actually I cannot say too much. But basically, no, we don't. Okay. And after all, remember this low pass, this edge preserving low pass filter is used to produce something for motion estimation only. In this so far over here. Okay. So as a result, even if you lose a little bit more detail, it's actually not the end of the world. It's not the end of the world.
So my question is this: do you know when you filtering start hurt the video quality?
Okay, when filtering will start hurting the video quality.
Yeah, I think it must be related to the QP or something.
Oh, denoising. When is it going to affect the? Oh, I see. Okay. I cannot say. Okay. I mean, this is a pretty long story. If you want to talk about that, coding, how coding is going to interplay with the denoising result.
Because it must be something about the bill rate, QP. Because we know, if you want to code as low quality video, you can denoise a lot, but still doesn't hurt.
All right. How about I draw something on the board? Is it okay? I find a pen. When you have noisy video, this is what you're going to get. Bit rate. This is PSNR. When you have noisy video, normally when you have clean video, we expect this, right? When the bit rate is high, PSNR is higher, right? This is what you expect for clean video. For noisy video, this is what you're going to see. This is what you're going to see, okay? Now, with no denoising, there's a certain region that you can just blindly compress it, and compression itself will kill the noise. Okay, because whether you have cleaner or noisy, you get the same thing. Compression will kill the noise for a certain bit rate. When the bit rate is high, the bit rate is high enough to preserve even the noise. And because of the noise, you cause the video to become bad.
So there's some optimal point.
Yes. Yes, we actually have some paper to derive this point. You can calculate this point. You actually can calculate this point. Okay, and that's good, all right? This is very, very good, because what that means is that if I know the bit rate, my bit rate is going to be lower than this point, forget about denoising. I just do compression and I got free denoising from the compression. Okay? But if I know that my bit rate requirement is higher, then what am I going to do? Well, if I know this point, then I would say that I would never, even if I want to be here, I would not want to give the bit rate to this guy, because more bit rate means I'm going to get bad performance. I'm going to only code up until here, and that's it. I would never allow my QP to go below a certain point so that I'm going to get worse performance and more bits. This is just stupid. With denoising, what will happen is that you are going to get something like this. With denoising, okay? You will not be as good as that, but you will be better than this point. You know what I'm saying? You will be better than this point because of denoising, okay? And that now there's a reason for you to increase the bit rate higher. With no denoising, there's no point to go beyond this point. All right? So that is the situation. Okay? All right. Okay, so coming back, when we do motion estimation, this is the cost function we use. Okay, J equal to, the first term is basically SAD. Okay, just SAD. Okay, plus lambda, this is the lambda rate, where the second term basically is V minus the P median predictor. The idea here is that we would like whatever motion vector you find, we would like it to be close to the median vector. Okay, in order that the motion field will become smooth. Okay. There's reason to believe that whenever you look at a particular block, okay, this block is part of a big region, and so this guy should be similar to the motion vector in the neighboring region. So it makes sense for the motion field to be smooth. And this will be especially so for large resolution, HD kind of situation. For low resolution, it's less true. Okay, for HD, it will be more true. Okay. So, and then basically we do two kind of search pattern, large diamond search and a small diamond search in different situations. Okay, and oh, I see. Another thing is that because we are doing, let me see, if this is frame T, this is T minus 1, T minus 2, T minus 3. What we are saying here is that at a certain point, if the mean square error is less than a certain number already, then perhaps you don't need to do anything further because it is good enough and the motion search can stop. Otherwise, you keep going. Okay, so something like that. Okay, all right. So this is the overall strategy. Okay, you start with m equal to 1. Okay, and then you search it. Okay, and if m equal to 1, this is what you do. If this is m equal to, for m equal to 2, you do this. M equal to 3, I think. 3, you do this. Okay. All right. For m equal to 1, we do free search. We do free search. Okay. We do a large diamond search starting from 0, 0. Okay. And then after the large diamond search stop, you go to small diamond search. Okay. All right. And then the second thing we do here is that we also use the median predictor as a starting point and do small diamond search. Another thing is that we use the co-locator block from the previous frame. Co-locator block. PC. Yes, co-locator block, yes. Okay, and that start doing a small diamond search, okay? And basically compare the three guys and see which one is better and choose that as the motion vector, okay? And then for m equal to 2, then we just do a large diamond search from the PTT is the temporal predictor, from a temporal predictor, okay? And then you do the small diamond search. And then for the other guys, you use small diamond search from the temporal predictor or something like that, okay? So basically this is what we do in the search. And so once again, this is what we got, okay? We can get quite a bit faster than the original method. Now, mind you, this method uses brute force full search, okay? And once again, because of the presence of the noise, we found the fast method doesn't work, so we have to use full search for this guy. And so now we found out that, yes, it is possible to do fast search, okay? And this is the kind of speed we can get, okay? In order to do this, we will need to include a edge-preserving low-pass filter in it before we do fast search. Now the fast search becomes trustworthy. The result becomes more reasonable. Complexity-wise, we are quite a bit smaller, right? So, okay, and the speed up, okay, and the motion field becomes smoother as expected because of the SAD thing, because of the predictor. It tends to be much smoother, okay, and yeah. So the result is quite reasonable, okay. And the PSNR can be a little bit higher, okay? Okay, yeah. Okay, so now, so far I've talked about two things. Number one, I talk about the temporal deinterlacing framework using multiple reference frame to do denoising. Second part is that for the first part, we need to do motion estimation, and we blindly use full search. Second part, we try to do robust motion estimation, but fast and robust motion estimation. So we've handled two things. Third thing, okay. Now, so far we've been talking about denoising as a pre-filtering measure, meaning that you don't denoising is one thing, codec is another thing. They are separate, okay. But now here we're saying that is there a possibility that we can integrate denoising in the encoder? That means we do both things together. Okay, now the encoder is willing to do something for you. Okay, how is it possible to combine them together to do something reasonable? All right, can we do that? Okay, if you imagine, then can we, later on you should bear this in mind, can we do spatial filtering with encoder? Can we do other things with encoder? I'm not very sure, okay, but I tend to think that we perhaps are the only method that you can integrate seamlessly into an encoder. It turns out that we are doing exactly the original filter. The temporal filter, we are not changing. We don't modify it. We do exactly the same thing. And we can integrate it into the encoder such that if the encoder complexity is this much, now with denoising, the complexity is this much. You just increase a tiny bit, and you have the added advantage of denoising. Okay, all right. So we're going to show you how we can do this. Well, this is regular motion estimation, well, hybrid coding, okay, MPEG 1, MPEG 2, 264, everybody do this. Input video, you do motion estimation here, you subtract the prediction to get the residue, and then you do DCT quantization and stuff like that. And then here you do locally decode that and add it back to the predictor to get the reconstructed video. And so basically this whole thing is the decoder, okay, and so on. Okay, all right, now you see that we leave quite a bit of space here, because we're going to add something there, okay? When we say we integrate something, what we are saying is that we want to keep this whole thing, except that we modify a little bit such that we achieve the effect of denoising while doing the whole compression at the same time. We are doing denoising within the whole encoding loop, okay? All right. Okay, so we have two things. We integrate the denoising into video encoder. We also can integrate the denoising into the decoder. Okay, so VEID video encoder with integrated denoising, video decoder with integrated denoising. We claim that this is equivalent to cascade scheme, meaning that when we do integrated video encoding and integrated denoising, we are effectively doing this. We are effectively doing pre-filtering followed by encoding. we are exactly getting the same result. For this guy, we're exactly getting decoding plus denoising afterwards using our method. Okay, but there's a constraint, and the constraint is that in the past, remember there's a parameter m. You can use current frame, you can use 1 frame, 2 frame, 3 frame, and I recommend that perhaps 2 frame is good, right? Using this method, you can only use 1 frame. You cannot use 2 frame. You cannot use 3 frame. You can only use 1 frame using this method. Okay, so that means it's not going to be you're not going to get the maximum benefit out of,
Using a cascaded method or using an integrated method?
For integrated method, okay, you can do an equivalent to a cascade method, but with m equal to 1 only. We cannot integrate m equal to 2 and integrate it inside. We cannot do that.
You only have one reference frame during motion estimation?
Yes, p frame.
If you refer to multiple previous frames, then you can still use m.
Yes, you're right. Yes, you're right. Yes, exactly. You're exactly right, actually. Yes. For the case of p frame, we can only do m equal to 1. If you allow yourself to have 2 reference frames, then we can do m equal to 2, yes. Yes, exactly depends on how many reference frames you use for your motion estimation in your codec. You're right. Okay. Okay. Well, the denoise video is basically, if you look at it, if you recall the previous formulation, the denoise video is equal to the noisy video plus the prediction, okay, and plus some d, right? This is the original formulation, okay, multiplied by a certain weight, and this weight are obtained by LMMSE kind of thing, okay. Well, we can. This is what we're going to do, okay. We are going to add something here. We are going to whatever the residue is. This guy minus the prediction give you the residue. For the residue, we are going to multiply by a certain weight, and then add a certain DC to it. Oh. Yes, that's right. Oh yes, one thing. Another thing is that we are going to restrict ourselves to have only one weight for the whole block. In the past, every single pixel can have a different weight. Here, the whole block needs to use the same weight. I'm sorry, I forgot to mention this. So it's not fully equivalent. It's not fully equivalent, but quite close. Okay. Now, mind you, okay, with this modification, it is very, very simple. You know that motion estimation is very, very complicated. After you do your motion compensation, this is the residue. You multiply by simply a number, and then you just add a DC to it. So it's very easy. Okay. Actually, my student did not do it right. Okay, we should have put this after the DCT. Because DCT is linear, it's exactly the same. Whether you multiply before or after, it's linear, right? And DC, it turns out that when you add a DC, you don't need to add 16 numbers. You actually only need to add it to the DC value, so this is a little bit faster. So we could have put this thing right after the DCT, and it will be faster. Okay, exactly equivalent, but just faster. Okay, all right. And then for the decoder, oops. Oh, yeah, there's something like that. Okay, all right. Here, this is how we derive our method. Okay. Now, residue, let's imagine now we are trying to do this. Imagine now we are doing denoising followed by encoding. Denoising followed by encoding. Okay. In that case, let's imagine what is the residue. When I do motion estimation, okay, I'm going to have the current frame, I do a search in the previous frame, I find the best guy, I subtract them to get the residue, right? So the residue is equal to some denoise guy minus the prediction. The current frame has been denoised already. Right? I'm going to encode it, okay? Well, the current frame is basically equal to the current noisy video plus a weighted version of the prediction plus some DC, right? I mean, this is just the current frame denoise. This is how we write it, okay? And it turns out that, well, you see P here and you see P here. You can combine them together, right? So W1, W0 and W1 add together will be equal to 1. W1 and this guy, so this is W1 minus 1. So this is actually 1 minus W1. 1 minus W1 is actually W0. So actually, this guy can simplify into W0 Fn minus W0 P plus D, but Fn minus P. Fn minus P. What is Fn minus P? Fn is the original noisy video minus the prediction. In other words, if I just encode the original noisy video, what do I get? I would be using my noisy video minus prediction to obtain the residue. In other words, to do this cascade denoising followed by encoding, you're effectively just like you are encoding the regular noisy video, except that you multiply the original residue by a number, and then you add a DC to it. What I'm trying to say here is that if you do the cascade denoising followed by encoding, this is exactly equivalent to doing, forget about the denoising, just do encoding, but in the encoding loop, you multiply the residue by a constant, by W, and then add a D to it. The two things are equivalent, yeah.
I recall Charles made a comment on whether this basically work will apply for multiple frames, for example, for B picture. And now notice you explained the mechanism of this approach. I felt that it may not apply for B picture. Because if it's B picture, for example, if you have two reference frames, right? You have W1 and W2. These two numbers may not be the same. And the residual of B is calculated in some kind of fixed format. And this magic does not work, right?
Good point. Yes. So it will not be equivalent. It will still work, but it will not be equivalent to the M equal to 2 temporal denoising. Yes, you're right. It's
additional constraint on the W.
Yes, that's right. You're right. Yes, you're constraining that. Correct. Good point. It will still work to a certain extent. Okay?
It may still work. The prediction now will be a weighted prediction of 2 frames, and you subtract it from the original, so it becomes.
I think the complexity will be about the same.
Yeah, we're saying you could probably extend this to multiple.
Given the fact that, I think you will use B frame instead of P frame when B works better than P, right? In other words, when the B prediction is better than the P prediction. And I think this will only be true when you have good motion estimation for both of those frames. In other words, I think in that case, most likely, their weight naturally, when you use denoising, their weight will be very similar. In other words, we will probably be very close to the optimal situation for M equal to 2. This will only be true when B frame works, B block works better than P frame, P blocks, right? And this will only be true when you have actually good motion estimation correspondence. Otherwise, you wouldn't do it. Right? So in a way, this method should still work quite well. Okay, but I cannot. But you're right. Yes, I don't think it is equivalent. It's not equivalent. Yes, but quite close. Okay. All right. So basically, with these few simple lines, this established the correspondence between separate purely pre-filtering followed by encoding cascade version versus the integrated version. They are equivalent in this sense. All right. So that's good. And the beauty of this is that it is very, very simple. Very, very simple. In the DCT, after you calculate the residue and then you do the DCT, you just multiply by a simple threshold, simple scalar, this thing, and then add a DC to it. It's very, very simple, super simple, and you can get the benefit of denoising.
That means this can actually be absorbed into a quantizer. Right? You only need to modify the DC coefficient.
This is done before quantization. This is done before quantization.
I think you can just roll everything into the quantization step. You don't need to incur any modification at all.
Oh, I see.
But you will be putting more of conditions on the quantizer.
This value
that would be more gates.
For different blocks, different.
But for each block, you only need to basically modify the quantizer.
Yes, actually, true. Yes, right. Yes, I agree.
Just adding more F conditions at the quantizer for these blocks based on the calculation instead of doing any addition.
That's right. But once again, remember, doing this kind of denoising, you may lose a little bit of the detail in the video, right? We mentioned earlier on. So you may want to think twice before you do it. Okay, you're going to gain something, you're going to lose something. What you gain is that the file will be smaller. The file will be smaller. Okay, you're going to have denoising effect. What you lose is perhaps some small image detail that you want to preserve. So we do need to be wise in order to do that. But one thing, remember, if you throw away this guy, if you allow W0 to be equal to 1, you get back the original. That means you can perfectly preserve all the original detail you want. And using this method, you get a W0. And if you really want, you can use a brute force method and force yourself to get a value between the value I want and 1. And you can get, you can have a continuous tuning of whatever you want. It is possible. It is possible. Right. Whether you want to do it is something else, but it is possible. Right.
How many things you have remaining?
Sure. That's about it, I think. Okay. All that we will claim is that, hey, complexity is not very much. Okay, audio performance is good. And you can also do it basically and the quality is good too. Okay. Oh, actually, not only that. Okay, this picture is interesting. Almost done. What I'm saying is almost done. Okay. And this one says that if you look at this one, this is the original cascade method. This method actually is an integrated method. And you see that this one looks better than this. And you would say, how can this be possible? How can this be possible? You are doing integrated. I mean, we just said this is integrated. Why can this be better? Okay. We have a reason for this. Okay. And the reason is that in the original cascade version, what we're doing is that in the current frame, you have a previous frame. And all the previous frame has been denoised, right? They're quite clean. And so when you do weighted average, they are good, and I tend to give them more weight, right? So I got a certain effect. Well, in this scheme, we have the current frame, we have the previous frame. The previous frame has been denoised and encoded. So notice that they have been encoded as well. And encoding actually gives you some denoising effect as well. And so as a result, they are actually even more denoised than the original cascade method. So that's why putting it into the integrated version, okay, you have added benefit of even cleaner than before. So you have a potential to get something a little bit better, but probably losing a little bit of detail too. I don't know, right? But anyhow, when you do coding, you are going to lose some detail anyway. It is lossy coding after all, right? So yeah, so we don't need to beat ourselves to death. So sometimes it actually works quite reasonably well. So anyway, for our method, okay, motion estimation wise, we don't do motion estimation at all. But for cascade method, we still need to do motion estimation. So 0 complexity for motion estimation. For the filtering, it is a little bit simpler than the cascade method, and so the total complexity for us is very small. I think you can easily see that it is very, very simple. Okay. Now, when it comes to the decoder, it is also possible to integrate this into the decoder. The application of this is that perhaps nowadays we have all these DVD player, okay? The video has been already encoded by Hollywood, and I cannot change their video, okay? But it turns out that maybe their video is a little bit noisy, maybe, okay? Especially in dark regions, a lot of the rain, kind of very dark region, you may have a bit more noise to it, okay? And in that case, it is possible to integrate the denoising into the decoder also. It is possible to do that, okay? Basically, one thing we need to face is that the decoder loop by itself needs to be self-consistent. You cannot modify the decoder loop just like that, okay? Because otherwise, you're going to have drifting errors, okay? And so as a result, we leave the original decoder loop intact, but basically, we do a denoised version, and for the display, we don't display the original decoder thing. We apply this little thing and display only the denoised output, okay? And basically, we need to add a loop similar to before. We need to multiply by 00 and then add a D to it, okay? And basically, this is still within the same loop, but we need to attack this next to this guy such that we can generate something which has the denoise effect already. So it is possible. But you can see that we don't have as much advantage as before because this is a bit more complicated than the encoder version. Okay. So for the decoder guy, okay, Okay, for the decoder guy, the equations are similar. You can show that they are equivalent to m equal to 1 temporal denoising, cascade version. Okay, and let me see. Our complexity. Okay, remember previously our complexity advantage is quite a bit higher than the cascade version, but now we are not as the gain is not so big. It is a little bit smaller. Okay, but then we actually can get these denoising effects. So this is something to consider. Right? This is less attractive than the encoder actually, but still, for completeness sake, we also derive the integrated denoising into the decoder. Right? So it is possible to do that. Okay, so with that, I think I end the talk. Right? So maybe we can look at the demo again. Okay.
Do you have other content to show that's been denoised also?
Huh?
Do you have a different video to show?
Sure.
Than the one with a little more motion in it? Or?
Sure, yeah. I have Foreman.
The Foreman.
This is noisy Foreman, and this is denoise Foreman.
At the same time, let me mention that Professor Au will be here with us today. Any one of you want to talk to him afterwards? Please let me know. And I will try to see if I can squeeze a slot. The next slot is Walid, and you need to meet with me, right?
Yeah, we arranged that.
Do you plan to meet in the restaurant, or you need to?
You see noise?
We'll drive together. We'll pick him up and then
blocky noise. Blocky noise. Okay. And see the blocky noise here? So this happens when motion estimation doesn't work so well. All right, and so locally, this part is clean up, this part is not so clean up. So this method by itself has some problem and need to be combined with, I think, spatial method to make it better, something like that.
Did you experiment with some kind of real video?
Say that again?
Did you do any experiments with real video?
This is real video.
I mean, this video was added noise.
Oh, okay. Oh, yeah. Oh, okay, good point. Yes, we try to apply this to denoise some TV signal. It turns out in our lab, our TV's reception is very poor, and the TV is very noisy. We try to use our method to denoise it. Okay, we found out that we can only denoise it to a certain extent. We cannot completely. Analog TV. Analog TV very noisy. You've seen those analog TV, very noisy ones. Okay, and we try to use this method to denoise that thing, and we have some effect, but we cannot get something as clean as this. It is super noisy, and it is less noisy, but.
I'd be interested to see webcam
Because that's my experience is that usually for artificial noise, it's really easier. I mean, the effect is better compared with the real noisy video.
Time consideration, let's thank Professor Orr for his inspiring